Okay, so I'm going to talk about proving your code correct in Lean, which is a proof assistant. So I'll start by first with a disclaimer. This is a talk given purely in a personal capacity. It has nothing to do with what I'm doing at work. So let's start by saying you could use fancy features of Haskell to kind of prove your code correct. Why might you not want to do that? Well, here's one reason. So we can define a type that says two types A and B are equal with a referral constructor that says they're equal. And then we can prove that string is int by defining a function like this. And you can do the exact, you do the exact same thing with any two types. This is bad. This means that Haskell is unsound as a proof system. So let's look at Lean, because Lean has termination checking, so that can't happen. That particular problem can't happen. It also has type classes, which I'm going to show in the demo in a minute. And so that means that you can fairly easily translate some short bit of Haskell code into Lean. Obviously, the syntax is going to be a bit different, but there wouldn't be too much messing around with trying to re-represent type classes. And you know, basic core features of Haskell like that. It has fully fledged dependent types, unlike Haskell. It has editor support for Emacs and VS Code, and I'm going to show you with Emacs. It has 4 ways of writing proofs. So you can write proofs using raw terms, which is basically like writing Haskell code, or you can write in a some sort of traditional proof style, like mathematicians might use, a calculational style, where you say x equals y equals z, therefore x equals z, and a tactic style, which is kind of the most powerful because it allows you to use the full automation power of Lean and write your own tactics. It also has some libraries which might contain things you wanted to prove that are already proved. And one thing I particularly like about Lean is proof irrelevance, which says basically that if you have 2 objects and they both contain proofs, but different proofs of the same thing, and everything else is the same, then they're basically the same. And that's true definitely in Lean, so no matter how different your proofs can be, or if they could be different, Lean doesn't care. So that's really convenient. You don't have to mess around with proving that proofs are equal, because we don't care. However, Lean doesn't have program extraction, so you can't just extract some code to Haskell and run it. That would be really convenient, but it doesn't. And it doesn't have back compatibility. So in the new version, it'll probably be all different and all your proofs will break, but let's hope not. So in the demo, I'm going to show a very simple example of a function. I won't show you the whole thing, but because there's various proofs involved, but I'll show you some core parts. And what it's going to be is a function that takes a graph, here in the example with 3 nodes and edges between them, and what I've called a defining set, which is nodes 1 and 2. And it's going to partition this graph into 2 subgraphs. One that contains the defining set of vertices, which I call the matching set, or the matching graph, and the other contains the other vertices and the edges between them. In this case, there are no edges from 3 to itself, so that's just a graph with a vertex and no edges. So we want to write this function that will work for all possible inputs. I'm going to prove that it will work. So this is the Emacs mode. I'm not going to go through the whole file. Got some bureaucracy at the top, but I'm going to go through the definitions because the definitions are the things we're talking about. Because when you're proving some code correct, it's very important to understand and get right what you're proving, not just to get the proof right. Because if you write a proof that's for something that is not actually what you want to prove, you've kind of wasted your time. So I'm going to cover that as well. So a finite directed graph I'm defining as a finite set of vertices where all the members of the finite set are in some type alpha. So this is basically like a set type in Haskell. And an edges function which given a vertex alpha, will give you all of the vertices which the edges out from that vertex lead to. So it's a directed graph, so they will lead in a particular direction to another vertex. And then we've got a proposition, which is something we have to prove, which basically says that for any vertex, if you call the edges function, you're always going to get vertices in the graph. Otherwise, it wouldn't make sense, because you'd have pointing to something that's not in the graph. Now, for all the remaining definitions, I'm going to introduce kind of like an implicit parameter called g, which is just a finite directed graph. That's just so I don't have to repeat myself. Then I'm going to define something which is quite convenient for correctness, which is a subtype type, which is basically a vertex of graph G. And that's basically saying it's an X of type alpha, that's inferred, such that X is in the set of vertices of G. You might notice here an interesting use of dot. This is not the same as the Haskell dot operator. This is actually more like the Scala or Java dot operator. And I know that might be a bit heretical to functional programs, but that is actually really useful in this context. So then we define an induced subgraph, which is a graph and has vertices which are a subset of the parent graph. And we also want the edges to be, basically, when you call the edges function on the subgraph, that should be the result of intersecting the parent graph's edges function result with the vertices sets of the subgraph. That's just to ensure that you are picking out the right edges. Then for a partition, which is what we're going to return from our function, we've got matching, non-matching subgraphs. We want two conditions basically, so that the partition has got to cover the entire graph. All the vertices have got to be in the all the vertices have got to be in the graph, and also disjoint, so that we don't have any vertices that are in both subgraphs. Now, this is the actual function. So it's taking a decidable EQ, which is like EQ in Haskell. It's taking our defining set, which is the argument, and it's returning the partition type. Now we call a bit of bureaucracy here, which I'm not going to go into, just to get things in the right form. And then we start to define our matching type, matching graph. So that is a finite directed graph with the defining set being the vertices, and the edges function being, for some x, the edges of x in the parent graph intersected with the defining set. And then now we need to do our first proof, which now we can look over here. This is the goal. This shows you what you have to prove. And very quickly we can introduce the parameters into the hypothesis space, which is before the turnstile, and then apply a standard mathematical theorem, which I'll just visit that now to show you it. It just says that if you intersect two sets, that is a subset of the second set. So it's basic sets theory. And that completes the proof. And the nice thing is that the other two proofs we have to do for this structure, we can just do with automated tactics. So we don't even have to think about them. We just need to plug in those tactics, and away we go. Yeah, so hopefully that gives you a brief flavor of proving with Lean. Unfortunately, I don't have time to go through the whole file, but I encourage you to check it out, try out Lean.
Cool, thank you. Unfortunately, we don't have time for questions on that. Next lightning talk is going to be